Before we fully develop the idea of energy, we're going to have to talk about something called work. Work is done on an external force acting on a system, transferring energy as the system displaces. The greater the force, the greater the transfer in energy. Also, the greater the displacement, the greater the energy transfer. The definition of work. Consider an external force F acting while the system undergoes a displacement d. If the force and displacement are aligned, and this will be really important, if they point in the same direction, then we define the work done as the work equals the force times the distance, or W equals FD. Right? At the moment, we're just making this definition, and I'm not telling you why we would define it that way, although it will end up being very useful. And it is really important that we have this. So some important restrictions are the force has to be constant in both time and space. The force and displacement must have to be exactly aligned. In other words, I have to move to the right and also push it to the right, or move upward and push it upward. And then also the displacement must be along a straight segment. Later on, we're going to broaden our definition to allow relax each of these. So this is what I often call the naive version. The simplest and most simplistic form. And as a student, be aware the students often memorize that and then use it when it's not really applicable because they forget these caveats and that this is really a shorthand to indicate some other stuff. All right, from the definition, the SI unit of work has to be 1 Newton times 1 meter, because it's a force times a distance, or 1 Newton meter, which is sort of duh. We always write it as Newton meter and not meter Newton, because the other way, you could conceivably, if you write it as a meter times a Newton, which is certainly algebraically allowed, you could misrepresent that as a millinewton and get people confused. So we always write it as Newton meter. That's not a graded thing, but it is the convention. The Newton meter comes up so often that it gets its own symbol called the joule, which we symbolize by capital J. And so 1 joule is 1 Newton meter. Since work is the transfer of energy, the unit for work must also be the unit for energy. That is, energy must be measured in joules, and that's true. Lifting your Chromebook 1 meter in the air gives it about 15 joules of gravitational potential energy, and you do about 15 joules of work on it. All right, very simple. How does this show up as a problem? Sarah pushes a crate along the floor at constant speed by exerting a constant force of 70 newtons on it. How much work does she do in joules in displacing the crate by 3 meters? And again, we just go back to our definition, say the work in this case, where the force is constant and along the motion, is going to be the force times the distance, or just 70 times 3, or 210 joules of work.